Okay, this video will be shorter, I promise. I want to show you how to check assumptions for the significance test of the correlation coefficient, and then also walk you through how to write an APA-style report of correlation results. Okay, so checking the assumptions of correlation analysis are a little bit different than the assumptions we learned to check in the tests like ANOVA and the t-test. And so I have this little table here that shows you what the assumptions are, how to check them in Jamovi, and how to interpret them. Okay, so we are actually going to just kind of go through, we're going to go through this process as we kind of work on this research question. Okay, so I'm just leaving that there. I'm going to come back to that in a moment. So I'm going to put everything together for this specific research question, which is going to be using the data set we started looking at for the last video. And that question is the amount of sleep that Dan's baby gets related to how grumpy Dan is the next day? Okay, so there's kind of three parts of doing this. And the first is to generate the mean and standard deviation of the variables. So let's pull our data set back up here. All right, so we're going to get the mean and standard deviation of Dan sleep and Dan grump. So we're going to go to analyses, exploration, descriptives, Dan sleep. Oh, sorry, no. Dan's baby sleep. So baby sleep and Dan grump. And we are just going to look at the mean and standard deviation as the first part of our analysis, right? So we're just noting the average number of hours of sleep the baby got, look at the standard deviation a little bit to get a sense of the spread of the distribution, and doing the same thing for Dan grump. Okay. Next thing we're going to do is generate scatter plots and R, and also a p-value for R. So we know how to do that by now. We go to regression, correlation matrix. Remember the research question is baby sleep and Dan grump. We're going to flag significant correlations. That just makes it easier. That's actually a really good technique. I mean, if you're not sure about interpreting the p-value in relation to the significance level, you know, a good check of that. If you check off flag significant correlations, and you know if your correlation is flagged like this is, then it has to be significant, right? So it's just a way to make it very easy for you to interpret by checking flag significant correlations. Okay, so we've got the scatter plot, and we have the R value, which is negative 0.566, and the p-value, which is less than 0.05, and it's got asterisk, so we know it's significant. And so that's like kind of the meat of our analysis for this correlation. Check the scatter plot, you can see that, yeah, it definitely looks like a negative association, and it is, you know, it is a fairly strong association. But if you think about how the dots looked for the variable that or for the correlation that we looked at before, I just want to show you something just so you can see. So remember how we talked about the relationship between Dan sleep and Dan grump was stronger than the relationship between baby sleep and Dan grump. And I just kind of want to show you this, right? So the relationship between Dan sleep and Dan grump was really strong, right? Negative 0.903. And look at how, so this is Dan grump and Dan sleep. Look how tightly clustered the dots are around the line there. They're tightly clustered together. Okay, so that's just a visual depiction of the stronger relationship, or the larger relationship for Dan sleep and Dan grump as compared to baby sleep and Dan sleep and baby sleep and Dan grump. Okay, but here, sorry, that was just a bit of a tangent. We are going to put Dan sleep back in here because for this research question, we are looking at the amount of sleep that Dan's baby gets in relation to how grumpy Dan gets the next day. Okay, So now we're going to check assumptions. This is where we're going to turn to the table here. Okay, so the first assumption of a correlation analysis is normality. It just means that both populations follow a normal distribution. We're going to check this in Jamovi following these instructions here. You will be familiar with this test from the t-tests and the ANOVA that we've been doing. You've learned that the Shapiro-Wilks p-value is what we look at, what we have looked at, what's been automatically generated for us in the t-test in order to check that assumption. Correlation, we're not going to get it automatically from the correlation output. We have to go and look for it. Thankfully, it's really easy to do. And so we just go to exploration, descriptives, enter our variables, baby sleep, Dan Grump in the variables window, and see how there's an option here under normality, Shapiro-Wilk. If you just check that box, it will add to your output, see at the bottom, Shapiro-Wilk. So just be careful because you are, so how to interpret, you are inspecting the Shapiro-Wilks p-value, okay? Not the Shapiro-Wilks W, okay? Don't make that mistake. You're looking at the p-value, Shapiro-Wilks p. And just as we've been doing for our other hypothesis tests, we want this p-value to be large, to be greater than 0.05, to be a non-significant p-value. And so if, as in this case, we see that the p's for both variables are greater than 0.05, that tells us that the assumption of normality has been met. So we're good for that one. The next two assumptions are homoscedasticity and linearity. So homoscedasticity is just a kind of fancy word for saying that we're assuming there's an equal distribution of each variable at each point of the other variable. So that means, in the scatter diagram, the dots should not be more spread out at one point of the chart than another. Okay, and so we're going to be looking at the scatter plot, and we're looking for this pattern here, right? That the dots shouldn't be more spread out at one point of the chart than another. And so we're going to look at the scatter plot, and sometimes it is honestly hard to tell. Okay, this looks not too bad. Okay, this looks not too bad. See how there's, the dots are kind of spread out across the entire length of the chart fairly equally, maybe a little bit more spread at this point than at, say, this point of the graph. Let me show you an example of something that would be really obviously violating that assumption. Okay, so just to contrast this with the example that we're working with, here's an example of a scatter plot where that assumption has clearly been violated. So see how here's our scatter plot, right? And see how the dots are very tightly clustered around the line, kind of towards this area of the chart, but the dots get more spread out from each other the further you go along the x-axis. So it's almost like a fan spreading out. And that's a very obvious example of this assumption being violated. Okay, what you want to see is, right, the scatter diagram, the dots should not be more spread out at one point of the chart than another. And I'd say this is kind of approximately what we have here. The third assumption here, linearity, we're also generating a scatter plot and inspecting it for linearity. Essentially, we want to kind of get a sense that the relationship between x and y is linear. And so, again, sometimes it is hard to tell from just a visual description or from a visual depiction, but just kind of do your best and try to, get the sense that there's not a clear, for example, curvilinear association between x and y. If the relationship between x and y seems kind of approximately linear in terms of the line you might draw through the dots, then that assumption has been met. Finally, the assumption of independence, which is that the individual cases are independent of each other. Okay, so that means like in a sample of 100 people, you don't have, siblings from the same family taking part, right? So say if you like three, you've got say 3 people of that 100 that are siblings, another 2 people that are also siblings. You've got another family, so the data includes 4 people who are also siblings. That's a case of dependence because their scores would be dependent on each other. Okay, so this is rare to see. I mean, I'm not going to give you an example like for the assignment, for instance, where the assumption of independence has been violated. And so there's not really anything to check or generate in Jamovi for this assumption. You should just be able to tell from the description of the research question and the participants whether this assumption has been met. And like I said, it would only be violated if it was clearly the fact that within the sample, there were kind of groupings of scores that would be dependent on each other. So kids from the same classroom, people from the same family, that kind of thing. Okay, so there we have it. We have our assumptions, and in this case, all of the assumptions have been met. And now we're going to write up our APA style report. Okay, so this is following a very similar formula that from what you've seen already this semester. There's a couple of differences because this correlation analysis just looks a little different than the ANOVA and t-test type reports. So let's see here. So we are just starting by summarizing our research question as we're used to, describing the variables and how they were measured, reporting the sample n, the mean and standard deviation for all variables, report that the correlation coefficient was calculated and a significance test performed, reporting R and its p-value, whether that was significant, and then R in terms of strength and direction, and the nature of the association. So let's, I just want to go through with you what these points look like in the example we're working with here, which is a research question looking at the association between how grumpy Dan is and how long her baby sleeps. So the research question is that a researcher, Dan, was interested in whether how grumpy she is related to how long her baby slept the previous night. So for 100 nights, she records how long her baby sleeps and how grumpy she is the next day on a scale from 0, which is not at all grumpy, to 100, which is extremely grumpy. And actually, I should probably put in there how long her baby sleeps in hours. That would be a more precise description of the variables and how they were measured. And so the sample n is a little bit different in here because we don't have 100 different people, we have 100 different nights, right? So for 100 nights, that's how we're reporting n. Reporting the mean and standard deviation for all variables, right? And you always want to put it in terms of, what the mean means, right? So we've been doing this throughout the semester. On average, Dan's baby slept 8.05 hours per night with a standard deviation of 2.07. So this is what you want to write, not the mean for baby sleep was 8.05. SD equals 2.07. Okay, so that, reporting the mean of baby sleep was 8.05, that's technically reporting the mean, but you can see how phrasing it like this is just much more clear and easy for an audience to understand. Okay, then we do the same thing for the grumpiness. And again, notice that, so I'm not just saying Dan's average grumpiness was 63.71 and the standard deviation. It is easier for the reader to understand if you say, Dan's average grumpiness on the 0 to 100 scale, kind of reminding them again of the scale, what the average was. Okay, so that's mean and standard deviation. now you're going to do this part here. So you're going to say the correlation coefficient was calculated along with a significant test of the correlation. Just as before, you're just reporting what test you used and your significance level and whether it was one or two-tailed. Now, for the most parts, as I said in lecture, when you're looking at a correlation analysis, you are going to be doing a two-tailed analysis. Like Jamovi, I don't think even gives you an option, right? It's not like it was with the t-test where you could click off whether you were doing a one or two-tailed test and in what direction. Here we just get a p-value, and that p-value is the two-tailed p-value. Okay, so it kind of goes without saying, but just re-report it anyhow. And alpha is 0.05. So we're saying, here we go. Okay, so we report that it was calculated, and now we say, we're reporting R and its p-value and whether the correlation was significant. Here's what this looks like. The correlation was significant, right? And then just somewhere in that sentence in brackets, you're reporting the exact R statistic and the p-value. Okay, sorry, I could change that. I don't know why that was positive. It's a negative association. Okay, so after you're reporting the R value, the p-value, and saying it was significant, and then you are reporting or interpreting rather the correlation coefficient in terms of strength and direction and saying something about the nature of the association. So here's what this looks like. It was a strong negative association, okay, indicating that the longer Dan's baby slept, the less grumpy Dan was the next day. Right? That's the part where you're interpreting the nature of the association. Here's something that I also want you to do. Now, this particular point may or may not always be part of a formal APA style results report, but I think it's important for you to do as you are kind of learning about the correlation and reporting the correlation and really getting in the habit of thinking about always reporting all of the possible directions of causality, because that is really the most honest and truthful way to interpret a correlation coefficient. Otherwise, people may be led down causal thinking pathways that is really not appropriate. So here we say, it is possible that less baby sleep caused lower happiness for Dan the next day. Okay, so this is where we are acknowledging that it is possible that X caused Y, right? It's possible that less baby sleep caused lower happiness for Dan the next day. Note that the actually Y causing X in this example is not possible because X was measured before Y, right? So if X is measured before Y, then, or sorry, if Y is measured, sorry, if Y is measured before X, then it can't have caused X, right? So if Y is how grumpy Dan is the next day, that is not possible for it to cause how long Dan's baby slept the night before, right? So the only other possible direction of causality is that there's a third variable, such as sickness or maybe busyness in the family, that may be the causal factor. For example, if there's a flu going through the family, this could be the causal factor of both of those variables, right? If you have a flu, then this is causing your baby to get less sleep and for the parent to likely be grumpier. All right, so check, indicate all directions of causality. Next, you're reporting if the assumptions were met. Okay, so for normality, you're reporting those Shapiro-Wilks p-values. For assumptions of linearity and homoscedasticity, you are indicating that you inspected the scatter plot and whether you ascertained that the assumptions were met or violated based on the scatter plot. You don't really need to report formally on the assumption of independence. It's, like I said before, it's inferred or assumed based on the research design. So we don't really say anything for that assumption in the report. So here's how I've worded the other assumption checks. So we say the assumption of normality was met for how long the baby sleeps, right? And then I'm just reporting that Shapiro-Wilks p-value, right? Baby sleep and Dan's grumpiness. And I'm also reporting the Shapiro-Wilks for Dan's grumpiness. All right, the p-value there is 0.122. We say an examination of the scatter plot indicates the assumptions of homoscedasticity and linearity were met, and there was approximately 100% power in this analysis to detect a large effect. And I just want to remind you that the power tables for correlation analysis are not in the textbook, right? I got this from somewhere else, and so they are only on the handout from November 22nd. I'll pull that up here so you know what I'm talking about. Okay, so that is this handout that I'm referring to. Remember, we calculated correlation coefficient, the significance testing, and here are our power tables. Okay, these are from the sister textbook to our textbook. Oops, there we are. And so, as per usual, we have these tables, and we have to indicate what effect size we're referring to, whether we have a two-tailed or a one-tailed test, and the total N. Okay, and again, you can see these numbers are all power values, right? They're proportions, interpret them in percentages. You can see that kind of all else equal, as effect size increases, the power number increases, right? The probability that you're going to find an effect if it is there increases with increasing power, and also kind of all else equal with increasing N, right? You can see you go down the columns, the larger N is, the higher the power value is there. So this is just like the other tables we've seen. We have a large correlation, right? Because it was over negative 0.50. So if we have a large two-tailed test, total N is 100. And so it's, power is nearly 1 or 100. And that's what we report. So we say there's approximately 100% power in this analysis to detect a large effect. Of course, if we had insufficient or less than 80% power, we would go to this table here to determine how many participants we would need for 80% power for a small, medium, or large effect. Okay, so that is all for correlation. Your assignment 9 instructions are to go and open another data set, take a look at this very, very simple research question, then do the same things with the variables in this data set that we just did with the variables in the parenthood data set, generating the scatter plot, correlation coefficient, the p-value, copying and pasting your output, and writing up the results in proper APA style format. So just following the guidelines that I have here. And that's all.